Okay, let us now continue with our discussion on differentiating algebraic function. In this lesson, we will be dealing with the more complex types of algebraic functions, and at the end of this lesson, you must be able to differentiate complex algebraic functions by applying the appropriate differentiation rules. Algebraic functions are not limited to being a constant function or just a power of x or a product of simple polynomials in x or ratio of polynomials in x. At times, we deal with a more complex form of a function. Thus, when differentiating functions of this form, we make use of what we call the chain rule. If g is a differentiable function at x, and if f is also a differentiable function but at g of x, then the composition of f to g is differentiable at x. Moreover, if y is the f function of g of x, where we let u be g of x, then we can write y as the f function of u, and that the derivative of y with respect to x is done by multiplying the derivative of y with respect to u with the derivative of u with respect to x. This is the chain rule for differentiation. So that when you are given, say, a power where the base is not simply x, but some functions in x, differentiating a power of the form u to the n with respect to x can be done by first differentiating u to the n with respect to u, giving us an n times u to the n minus 1, and then multiplying this with the derivative of the base with respect to x. The chain rule for differentiation can be applied in differentiating a radical of index equal to 2. That is, if u is a differentiable function of x, then the derivative of the square root of u with respect to x is given by the ratio of du dx to the product to the square root of u. That is, the derivative of a radical whose index is 2 is a fraction whose numerator is the derivative of the radicand and whose denominator is twice the given radical. So we have the derivative of the square root of u with respect to x given by du dx divided by 2 the square root of u. Generalizing on the rule to differentiate a radical with index other than 2, meaning differentiating the nth root of u. If we take n to be a positive integer and u is a differentiable function of x, then the derivative with respect to x of the nth root of u, or u to the 1 over n, would be given by 1 over n times u raised to exponent 1 over n minus 1 times the derivative of the base u with respect to x. Okay, let us now have some examples illustrating the use of the differentiation rules that we have just discussed. In number 1, we define y the fourth power of 5x squared plus 10x plus 5. This function can be fitted to the form u to the n, where our u is 5x squared plus 10x plus 5 and n is equal to 4. In differentiating a u to the n, its derivative is given by n times u to the n minus 1 times du dx. So that if we are going to apply that to this given function, then the derivative y prime would just be equal to the exponent 4 times the base 5x squared minus 10x plus 5 raised to exponent 4 minus 1, or we have a 3. This is to be divided now by the derivative of the base 5x squared minus 10x plus 5, for which the derivative of 5x squared is just a 10x, and that of negative 10x is negative 10. If we are going to factor out 10 from these terms and multiplying that with 4, then y prime now would be given by 40 times x minus 1 times 5x squared minus 10x plus 5 raised to the third power. Number 2 example is a square root function, defining y to be equal to the square root of 4x minus 8. So if you recall, the derivative of the square root of u is given by du dx divided by 2 the square root of 2. In square root of u, In this particular example, we have the square root of 4x minus 8. Our u here is 4x minus 8. So that if we are going to differentiate the given function, then in the numerator will just be the derivative of 4x minus 8, which is just equal to 4. And this is to be divided by 2 times the square root of u. Or we have 2 times the square root of 4x minus 8. Now this given expression here can be simplified further. What we can do is we can rationalize the denominator, multiplying this given fraction with the ratio of the square root of 4x minus 8 to the square root of 4x minus 8. The square root of 4x minus 8 when multiplied with another square root of 4x minus 8 would rationalize the form of the denominator, giving us now this particular expression. So y prime would equal 2 times the square root of 4x minus 8 divided by the product of these two factors, which is just equal to 4x minus 8. Okay? Or from these terms of 4x minus 8, you can factor out a 4, expressing that denominator as product of 4 with x minus 2. So that y prime can now be simplified into the ratio of the square root of 4x minus 8 to 2 times x minus 2. This is after dividing 4 by 2. Example number 3 would illustrate how to use the differentiation rule to differentiate an nth root of u where the index is different from 2. Here we have y define the fourth root of the product, 3x minus 2 times 2x plus 3. Algebraically, this is equivalent to the form y is equal to the quantity, the product of 3x minus 2 times 2x plus 3 raised to exponent 1/4. So in this form, we have a u to the 1 over n. And that the derivative of u to the 1 over n would just be equal to 1 over n times u to the 1 over n minus 1 times du dx. So if we are going to apply this rule here, y prime would equal 1 over n, so 1/4, times the base raised to exponent 1/4 minus 1 times the derivative of the base. The base is a product, hence the derivative is obtained by applying the product rule. So the derivative of 3x minus 2 times 2x plus 3 would be given by the sum of the following products. The factor 3x minus 2 times the derivative of 2x plus 3, which is just a 2, plus the product of the factor 2x plus 3 with the derivative of 3x minus 2, which is just a 3. So if we are going to simplify our y prime, by working now on the product of these factors and then combining similar terms, y prime would be equal to 1/4 times this product of 3x minus 2 times 2x plus 3 raised to exponent negative 1/4. that is coming from 1/4 minus 1. And then this particular expression here will simply give us 6x minus 4. That's the product of 3x minus 2 with 2, and a 6x plus 9 coming from this product. So that our y prime would now be given by 1/4 times the product of the factors 3x minus 2 times 2x plus 3, the quantity raised to negative 3/4 times 12x plus 5, which is the simplified form of this particular expression. Now, writing this in a form where the exponent would be positive, y prime then would equal 12x plus 5 divided by 4 times the product 3x minus 2 times 2x plus 3, now raised to the positive exponent. So in summary, when you are differentiating complex algebraic functions, then we can easily determine the derivative of this given function by applying the chain rule for differentiation.